Hi, and welcome back to the challenge videos for Physics 102, Introduction to Electromagnetism here at McGill. So this question we're going to look at this week is question 3.4 on the slides, but we're first going to look at the overall system that I've set up. So we have our three charges. We have two charges with a value q, which is plus 10 to, times 10 to the negative 19 coulombs, and one value here, little q, which has a value of minus 1 times 10 to the negative 19 coulombs. So the distance between the two charges, big Q, is L. The distance between each charge, big Q, and charge little q is h along the hypotenuse, and we have an angle theta here. We set the origin to be there at the center where the two lines intersect, and what we can see is that the two charges q are separated by an equal amount in the y direction from the charge little q. So the first thing we want to do is think about this conceptually. So in this video, I'll go through the conceptual arguments of how this is going to work. In the next video, I'll do some calculations. So first, what we're going to notice is that the q is equal in magnitude, and they're both positive charges. Little q is a negative charge, so it's going to feel an attractive force to both of the charges big Q. However, the y direction is going to cancel out. That should be fairly clear because it's evenly spaced. So if you actually do this out, you'll find that the contributions will be equal and opposite, meaning that they'll cancel out, leaving us only with an x direction. So since it's out here to the right, and it's going to be attracted towards them, both this q and that q, it's going to feel an overall force to the left in x, but no force in y again. Okay, so now let's think about it if charge little q was over here, to the left of the two charges big Q. Well, the y forces are still going to cancel out, but the attractive force in the x direction is now going to be to the right. So what we have is, if it's to the right, it's going to move towards the center, and if it's towards the left, it's also going to move towards the center. So what we have here is simple harmonic motion. So let's look at simple harmonic motion briefly. The simplest kind of simple harmonic oscillator is a mass on a spring, which you saw in Physics 101. So let's draw that. So we have our spring and our mass here. And if we set x equals 0 for the equilibrium position, we have a maximum extent plus a and a minimum extent minus a. It's the same distance from that central point. Then what the spring is going to do is the spring is going to oscillate between the two of them if given an initial kick. So what that exhibits is a standard case of simple harmonic motion. What we're going to look at in the next video is how to actually calculate the effective spring constant of this system. So if we look at this, it's going to exhibit simple harmonic motion, which means that it can be thought of like little q is on a spring. So we're going to find the spring constant that makes this all possible.